Hello, and welcome to Agrosive Physics. Today is day 77, and what we're going to do today is start discussing waves. Now, the course at this point is going to switch dramatically. The entire first half of the course was about mechanics, and what we tried to do is discover the motion of objects, typically how to describe them, which we'd call kinematics, and then why they move, which was dynamics. The course at this point switches to waves, light, and then eventually goes into electricity and magnetism. But at this point, we're going to discuss waves. Now, why would we start discussing waves now? Well, the most important thing is that waves act a little differently than particles when they're transferring energy. In fact, waves transfer energy without transferring mass. If I were to throw a ball at someone, I can impart energy onto that ball, and the ball would move across the room, and the person hopefully would catch it. Well, at the end of that event, I no longer have the ball in my hand. I've transferred energy, but I've transferred it with the mass involved. Now, waves, on the other hand, do not do that. The wave can transfer energy, but the matter stays where it is. In fact, we send that energy in different ways, sometimes through the air or sometimes through the vacuum of space, without changing where the original matter is. In the example of water or air, we're vibrating the particles of air or water near where I begin the wave, and then that sends a ripple effect throughout the medium, in that case either air or water, and that energy will be moved to the end point. It could be at the end of a pond or a lake. It could be the end of the seashore if we're talking about an ocean. Or if it's sound waves, it will be that the sound travels to the person listening to the sound, or the event transfers from one place to another, but it doesn't change where the particles are. Most of the particles of air or water stay in the general vicinity of where they started. Now, in terms of a definition, we have a very specific definition that I looked up on Webster's dictionary to start us off. And the definition is as follows. A wave is a vibratory disturbance that propagates through a medium. Now, that in and of itself is a definition that I find a little bit of fault with because of the fact that it says through a medium. Waves don't always need a medium in which to travel. Now, first of all, vibratory. Well, that means the object vibrates. It moves back and forth. So when we're sending sound waves, we vibrate the air in front of us, and that causes other air particles to vibrate as well. And as the particles of air vibrate, they push the next particle in the line, and eventually the sound wave will travel from one place to another. On the other hand, light does not need a medium in which to travel. So we have a fancy name for light waves, and we call it electromagnetic waves. Well, they don't need a medium in which to travel. In fact, they can travel through the vacuum of space. But in terms of the definition from Webster's dictionary, we have the vibratory disturbance. Normally, the particles will just sit where they are. We cause a vibration. We cause a change in the environment that causes those particles to move. And it propagates, and that's just a fancy word for moves through, a medium. So the only thing that I would have fault with in this definition is that the medium is not necessarily involved. This would be true for what we call mechanical waves, which need a medium, such as sound or water. Without water, you can't have a water wave. However, you can have waves travel through space, and that's just a different form of wave itself. That being said, the most important part about waves in our usefulness here is that they can transfer energy without transferring mass. So that's the big difference between our energy chapter, which we just ended, and the wave chapter, which we're beginning now. So the fact that we can still have the particles near where we are changes that energy transfer. If you think about a whip being, whipped, what you can see is that at the end of that event, if I were to use a bullwhip and snap a twig on the ground or something like that, then that whip is still in my hand. I can send the energy through the length of the whip, but at the end of this, I still have the whip. With a ball, when I throw it, I no longer have the ball. I can't reset and then throw the ball again. I'd have to go and get it. So I'd have to expend more energy to get the ball. Now, waves have different types, and I already alluded to those at the beginning of this discussion. First of all, we have mechanical waves, and they need a medium with which to travel through. Sometimes the medium is air, sometimes it's water. It could be glass, it could be plastic, it could even be a piece of wood. If you knock on a door, you send that sound wave through the door itself first, and that door could be made of many different materials. And at the end of that journey, when it gets through the thickness of the door, then that sound wave will then travel through air. So sound waves can travel through multiple mediums until it gets to the person, in this case, if we're knocking on a door, the person that we want to hear the knock. So it doesn't always have to be a single medium in which the wave travels through. The material that requires a mechanical wave has to be bendable in some way or flexible. So if you have air waves, we're sending sound, the flexible nature of the air particles will be what we have in that case. Now, you may think that a door or a piece of steel isn't very flexible. And what's happening is the particles in the door, if it's a piece of wood, are actually vibrating inside the door and sending the wave that way. When it gets to the other end, it will then push the air particles at touching the door itself and then travel through the air till it reaches the next person or object that wants to hear that sound or is going to receive that sound. Sound waves will also bounce around the room, and we're going to have fancy words for that as we move forward. And I'm pretty sure you already know some of those now, but I'll leave it at that for this point. On the other hand, instead of mechanical waves, we also have what we call electromagnetic. Now, light is an electromagnetic wave, and it does not need a medium in which to travel through. Now, light is not just light that we see, visible light. It also has other forms. We're going to talk about the forms in more detail later, but light has many forms such as gamma radiation, or ultraviolet, or infrared. It even is in the form of microwaves. And radio waves are also a form of light. Now, we often think that radio waves are sound, but in fact they're not. Radio waves can travel through space. Sound waves, on the other hand, can only travel through a medium. So a sound wave is a mechanical wave, whereas radio waves are an electromagnetic waves. So we have two different types of waves, one that travel through a medium, that's mechanical, and ones that do not travel through a medium, electromagnetic. And electromagnetic waves are commonly known as light waves. Now, within that classification, we also have different types of waves in the method that they vibrate. There are three types, and we're going to focus mostly on two, but the three types are longitudinal, transverse, and surface waves. Now, longitudinal waves vibrate along the plane in which it travels. And the way we say that is the particles vibrate parallel to the motion of travel. We also have another name for longitudinal waves, and they're often called compression or pressure waves. Sound waves act in this manner. As I'm speaking right now, the sound wave is being traveled by pushing the sound, or the air in this case, near my mouth, and it's causing the air particles to vibrate. And they vibrate in a compression manner. So the particles near where I'm talking will push together and then spread apart. Push together and then spread apart as the sound waves travel. The key is that the vibration is parallel to the direction of motion. On the other hand, we have transverse waves, and those travel perpendicular to the motion. Perpendicular means they travel up and down as the wave travels sideways. Now, the bullwhip example that I gave before is an example of a transverse wave. As the wave travels to the left or right, the particles actually move up and down as they vibrate. On a small scale, water waves act as transverse waves. Now, if we think about math class, the sine graph or the cosine graph that were often used in math class are an example of transverse waves. That's a visual representation of the transverse wave as it travels. The third type of wave is actually a surface wave, and it's a combination of the two. Water waves on a larger scale are actually a type of surface wave. We also have earthquakes. As the wave travels in an earthquake, we have different types of transfer of that energy. And in some cases, the particles vibrate up and down and left and right at the same time. The net effect of that is that as the particle moves up, it's also moving to the right, and as it moves down, it's also moving to the left. So you have a circular pattern with surface waves. In this case, if you can think of a water wave in an ocean and you have the rip curl on the top of the wave, that's a good example of the surface wave and the fact that the particles are moving forward and up and down at the same time. So we have a circular pattern as a surface wave travels. In lab, we'll often use water waves with small amplitudes. They move very, very small distance from their rest position. So in that case, we can treat the water waves as a transverse wave. The water molecules will vibrate up and down, and the wave travels to the left or to the right. But the key, if you want to make it sound a little smarter, is that the particles are moving perpendicular to the wave motion. Wave travels horizontally, and the particles move up and down. The key to a transverse wave is that although the energy is being transferred sideways, the particle is only moving up and down. If you think about a wave at a sporting event like a baseball game, if someone's doing the wave or a group of people are doing the wave, they're moving their arms up and down, or they stand up and sit down, but they don't change where they sit. So the energy of that wave, although it's simulated, is moving around the stadium in a left or right manner, but the particles, the people involved in the wave, are only moving up and down. So if you think about a wave at a sporting event, that's a good example or a good analogy of a transverse wave. Now, a longitudinal wave, as it moves, it's moving kind of like an accordion. It's spreading like this as it travels. Well, we have names for when the particles are smushed together, fancy term, smushed, or spread apart. When they are moved closer together, we call that a compression. When they move farther apart, we call that an expansion. There's an even fancier term for an expansion, and that's called a rarefaction. So we have compression and expansion. And those are the types of motion that the particles have. They're smushed together, compressed, and they're spread apart or expanded. The key is that it's difficult for us to measure values such as amplitude with a compression wave because we're trying to figure out where the point of the compression is and where the point of the expansion is. Most often we'll use transverse waves when we're trying to understand different types of waves and their other characteristics. But for longitudinal, we have compression and expansion, and sometimes expansion is also known as a rarefaction. On the other hand, we have terms for the transverse waves. The top of the wave is called a crest. So if you think about a sine graph, you have a crest at the beginning of the sine graph. That's the top. The maximum point is the top of the crest. And then at the other end, as you continue the sine graph, perhaps as you go to 2 pi radians, after you get to the crest, you'll start moving downhill again, and then you'll draw the trough of the wave. So you have the crest, which is the top of the transverse wave, and then you have the trough, which is the bottom. If you listen to weather reports, you'll often hear the meteorologists talk about crests or troughs in the weather patterns. They're talking about high and low points of pressure. And as the winds are traveling, as the fronts are moving throughout the locations, the geographical locations, you have areas of high or low pressure representing the crests and troughs. Now, in the surface wave, as I said before, you basically combine the transverse and longitudinal manner of the waves. So you have longitudinal compressions and expansions, and you also have crests and troughs kind of combining. So the surface wave is going to produce circular motion for the particles involved. In all of these cases, the particles stay in the general vicinity that they started in. They just push the ones next to it, and then that wave pattern will allow the energy to move along the wave itself. So if we have longitudinal, it's compressing and expanding, and if we have transverse, it's lifting and lowering. So we have different analogies to help us visualize it, But the reality is the flexible nature of the material in which it's traveling will be either vertical or horizontal depending upon the type of wave. Now there's a few other terms that we'll talk about today, and there's not too much more for today's lesson, but we have a pulse, which is one single wave traveling, or we have a wave train, which is a continuous series of pulses. So as you send a wave, if you had let's say a bullwhip again, that would be sending a single pulse. If we continually oscillated, put your toe in the water and you continually moved it up and down in a lake, you would be sending out a series of waves, also known as a wave train. And the wave train is also known as a periodic wave as well. It's just a continuous series of pulses. So a pulse is one, and a wave train is many. So we have two different types of waves today. We have mechanical and electromagnetic. Mechanical need a material in which to travel. Electromagnetic do not. And then we also have three different types of waves within those classifications: longitudinal, transverse, and surface. An example of a longitudinal wave typically will use sound waves because they compress the air near them and expand. Transverse waves, we can think of a sine graph. We can think of the wave at a sporting event. We can think of a bullwhip because the wave travels left and right and the particles move up and down. If you are trying to wash your car and you have a long hose that you're trying to get around a tire, let's say it's stuck on the tire, you may send a pulse down the hose to get it unstuck from the tire. In that case, you send a single pulse. On the other hand, you can have a continuous series of, let's say, a continuous sound. That would be a wave train. You're continually sending the sound waves and compressing and expanding the air near the event that's causing the sound waves to be created. It could be a horn, it could be a siren, it could be a person just singing a single note in a sustained manner. So in conclusion, today we discuss waves. Waves transfer energy without transferring mass. That's the major difference between the typical things we've talked about before, where we transfer the energy and the matter. And then we have different classifications of waves: mechanical, electromagnetic, and then the types of waves that we'll deal with are transverse, longitudinal, and surface. In addition, we have a single disturbance, which we call a pulse, and a series of identical pulses, which we'll call a wave train. Today was day 77, and I thank you. This was a Gross of Physics. All right, to reiterate what we talked about today, we talked about waves, and they transfer energy without transferring mass. We have two types of waves that we discussed. We have mechanical and we have electromagnetic. Mechanical needs a medium. Electromagnetic does not. Electromagnetic waves are all different forms of light. This should not be a very heavy topic for you. We then went into transverse versus longitudinal. Transverse waves, the particles vibrate up and down and the wave goes left and right. So the wave moves to the right in this case, and the particles vibrate up and down. So the only thing that this particle will do is move up in this case. This particle will move up as the wave travels to the right. It's because what we need to do is look behind the particle. And what's coming behind the particle is a trough. So this part goes down. Same thing here. As opposed to longitudinal. Longitudinal waves compress and expand. It's not as easy to draw longitudinal waves. What I'm trying to show here is this would be a compression, and this would be an expansion. Fancy word for expansion is rarefaction. We also discussed, finally, we have a pulse, which is 1. Unlike medically, a pulse will be continuous, but in wave terminology, a pulse is one single crest and trough sent along a spring or maybe a whip or something like that. A wave train is continuous. So you have the difference between different types of waves. First, transfer energy without mass. We have mechanical versus electromagnetic. And then you have transverse and longitudinal. Transverse, the particles are perpendicular to the wave motion. In the longitudinal, they vibrate in the same direction. So as the wave travels left and right, the particles are vibrating left and right. They stay in the same general vicinity. They just vibrate back and forth. And that concludes some of the terminology we need for today. I thank you. All right, first we'll look at a transverse wave. And the key is that the transverse wave particle motion is perpendicular to wave motion. So if I have this slinky spread out, what I'll do is I'll send a pulse down, another pulse down, and another pulse. And what will happen is the wave will cause the particles to vibrate up and down as the wave travels left and right. Transverse. Particles move up and down like this, and the wave is traveling left and right. Transverse. All right, the next type of wave is longitudinal, and that's where the particles are parallel to the wave motion. So, as an example, we'll take the slinky, and I'll push the wave, push the wave, push the wave. And what you'll see is I'm sending a compression along the length of the spring, and it's bouncing back because I'm holding the other end. But the particles are in and out like an accordion, and the wave is traveling in and out. This is a compression wave. So as I push inward, what's happening is we're seeing areas of compression and expansion. This is like an accordion as I send the wave back and forth. I push it, the wave travels parallel. So the particles are moving left and right, and the wave moves left and right, parallel to the motion. When we have a pulse versus a wave train, that's a measurement of how many. I send one, that's a pulse. This would be a transverse pulse I'm sending. We have some reflection, but that's a pulse. I'm going to send one longitudinal pulse. I'm pushing the slinky, compressing a section, and the wave is traveling left to right. And then some reflection occurs. Here's a wave train. I'm sending a series of pulses, and I'm creating a continuous wave, also known as a periodic wave. Do the same thing with compression. And you'll notice there's spots where the compression stays consistent and other spots where the expansion stays consistent. So, pulse means 1, and a wave train is continuous. Difference between a pulse and a wave train.